Yes, am I audible, Harsha?
Yes, ma'am.
All right, in the last class, we had started with stress and strain. Both these topics we have completed. So stress is basically deforming force per unit area. So if the force is perpendicular, you get normal stress. If there is a change in shape, then you get tangential stress. And if there's a change in volume, you get volumetric stress. Then you have strain. Strain is a change in dimension by original dimension. So if length changes, we get longitudinal strain. If volume changes, we get volumetric strain. And finally, if the shape changes, we get shear strain. Now, see, Harsha, depending upon the ratio of stress and strain, we have few quantities. Before that, let us discuss what is meant by Hooke's law. See, when we are referring to Hooke's law, what is meant by it? Firstly, just understand what is meant by elastic limit first. See, there is a maximum value of stress that can be applied to the body, with that the body can bear. Otherwise, see, if a body has a tendency to regain its original shape back, it's not necessary, if for a very small object or a very light object, if I am applying a very heavy mass, so what will happen? Because of the heavy mass, the body's weight will be deformed and it will not be able to regain its shape back if the mass is very, very heavy. So it means the elastic limit has been crossed. This means elastic limit has been crossed. So maximum stress from which an elastic body will recover. That limit, that maximum limit is known as C. There is this maximum limit achieved. This maximum limit is known as elastic limit. If this is crossed, then body will become plastic. Body will never be able to regain itself back. So in order to, and for a body, in order to remain in the state of elasticity, it has to obey the Hooke's law. Now, what is meant by Hooke's law? Hooke's law basically says that, see, suppose this is a rod and the extension that has been produced is X and the deforming force is F. So Hooke's law basically says that this force, the applied force, which is the deforming force, this is directly proportional to the displacement or the change in length that has occurred. So if elastic limit is not crossed, whatever is the force applied, that is the deforming force, it is directly proportional to the change in the length of the wire. That is the extension which is produced. All right, so this is what is meant by Hooke's law. Now it says that Hooke's law, if you go into the details of Hooke's law basically says that stress is directly proportional to strain. Now see, if stress is directly proportional to strain, what can I do? In order to remove the proportionality constant, stress is equal to K times the strain. So if I bring it in the denominator, stress over strain is equal to constant, right? So this constant here that we'll be using, this constant, stress by strain, is equal to E. This is known as modulus of elasticity. This is known as modulus of elasticity. So if elastic limit is not crossed, stress will directly be proportional to the strain. This is the statement of Hooke's law. Fine. See, remember, if the value of this modulus of elasticity is greater, then it is very difficult to change the shape of the body and make it plastic. All right. So this is a very important formula. Depending upon this, you have 3 types of moduli of elasticity also. That I'll discuss it later. First, let me tell you the graph. See, This graph says what? Stress, see, stress is directly proportional to the strain. So with which amount the stress will be increasing, with the same amount strain will be increasing. So how do you calculate it? See, stress over strain perpendicular, see, stress over strain. This will give you 1 over tan theta. Look, stress is here, strain is the perpendicular. So this is the slope of strain versus stress graph. If you have stress versus strain graph, then it's easier. Here, stress by strain is equal to tan theta, which is equal to slope of the graph. So the way we have been performing simple linear equation, this is how stress and strain proportionality is indicated. Stress is directly proportional to strain. This is what you have to remember. And which graph is given? Is the graph between stress versus strain given, or the graph between strain versus stress is given? This you have to first identify. But this law will be the same. Now see, depending upon the types of deformities, what have we studied? There were different types of deformities, right? So different types of deformities produced different types of stress and strain. When there was a change, one component was there which was change in length, one component was there change in force, one component was there which was change in volume, right? So depending upon the changes, if stress are of different type, if strains are of different type, then moduli will also be different type. So if there's a change in length, then you get Young's modulus of elasticity. If volume changes, you have bulk modulus of elasticity, and if there's a change in shape, you get modulus of rigidity. So individually, we'll be seeing these three. First, write down these basics.
Ma'am, can you explain how we got 1 by tan theta in the graph?
See, how have we got 1 by tan theta is, see, stress is directly proportional to strain, and stress by strain is what? Is the modulus of elasticity. So if I want to calculate modulus of elasticity, I have to take the slope of the graph, right? In order to calculate the third quantity, I have to take the slope of the graph. Now when stress is there here, and how do we calculate slope of a graph? We calculate it using tan theta. So when stress versus strain is given, tan theta becomes stress perpendicular by strain base. So E is directly equal to tan theta. But if I draw strain versus stress, so what stress versus strain be equal to? See, this graph is strain by stress is equal to tan theta, right? See, perpendicular is strain, base is stress. But do we need strain by stress? Moduli of elasticity is, this is 1 by E. That's why in order to get E, we have reciprocated and written it as 1 by tan theta, which is the slope of this graph. Clear?
Yes, ma'am.
All right. Write down this. Hooke's law is important. Hooke's law is asked in the exam also. Hey, Harsha. Now coming to Young's modulus. So Young's modulus is, what did I say? Moduli of elasticity are what? They are the ratio of stress and strain. Now, depending upon the type of strain and the type of stress, you get a different type of Young's. You get a different type of moduli of elasticity. So when we take among the stress, we take normal stress, which was the change in length, and from the strain we take the longitudinal strain. When from the strain we take the normal stress, and from the longitudinal, see, suppose this is a rod and this is the elongation that has been produced due to presence of a deforming force. Now see, force, this is the area of cross section, right? This is A, and the force that is being applied is F. Force is F, and see, this is the elongation that has been obtained. And what was the original length? Original length was L. So Young's modulus, what did I say? Young's modulus is basically the ratio of normal stress. Normal stress means the change in the length to the longitudinal strain. So this becomes normal stress to longitudinal strain. Normal stress to longitudinal strain. Now, what is the formula for normal stress? Normal stress, you can say, or longitudinal stress, you can say. Remember, two terms I told you. So longitudinal stress or normal stress, both are same. So what was the formula of stress? Force per unit area. So the deforming force is F and the area of cross section is F. This will be the formula of normal stress. Now, what is the formula of longitudinal strain? Longitudinal strain is change in dimension by original dimension. So here the dimension which is changing is length. So what is the change in length that has occurred? Delta L, which is the elongation. And what was the original length? Original length was L. So now substitute these values in the Young's moduli formula. See, Young's modulus will be force per unit area, that is the normal stress, and delta L by L because of the longitudinal strain. So ultimately you get the formula FL by A delta L. This is the formula of Young's modulus. SI unit C. Can you tell me the SI unit for Young's modulus? SI unit for Young's modulus, Harsha.
Pascal.
Pascals, right? Because see, force per unit area, this has the SI unit of Pascal, and delta L by L is unitless. So what all things do we have from here? This is Young's modulus. F is the force, L is the original, delta L is the extension or elongation, and A is area of cross section. This is the formula that we'll be using. We'll see the questions also. First, you write down these theory portions, then we'll discuss. See, this question says that a composite wire of uniform diameter 3 millimeter consisting of copper wire of length 2.2 meters and steel wire of length 1.6 meter stretched under a load by 0.7 millimeter. So if two wires are there and this load is given, it means this is the combined load. When it is saying no, see how is the figure for this? Suppose this is the copper rod. At a fixed rigid end, copper rod is kept. And here this has been taken, this is the steel one. Now what all are the dimensions given? Copper, it is saying that copper's length is 2.2 meters. Length of steel is 1.6 meters. Right, this is exactly what has been said. 1.6 and 2.2, right? Now see, now this is saying that a single common deforming force is applied to both of them, right? Now elongation, change in length of copper plus change in length of steel. This is combined together and given to you as 0.7 meter. See, when we say Young's modulus for copper, it will be 4FL by A delta L. This is the formula. So force is same, length of copper is different, area of cross section is same. Both of them have the same area of cross section. Delta L of copper is there. When we write about the Young's modulus of steel, so force is same again, Ls and delta Ls. First take the ratio, because many things will now be cancelled then. So FLCU by A delta LCU into A delta LS by FLS. So area, force will be cancelled. Now if these are cancelled, what put in the values? Young's modulus of copper is given as 1.1 into 10 to the power 11. What was steel's given? 2 into 10 to the power 12. This is also 11. 2 into 10 to the power 11. 2 into 10 to the power 11. This is also 11. Length of copper is given as 2.2, right? Into delta L, leave it. Delta C. Okay, delta L, let's write. And what is LS? LS is 1.6. Now, LS is also there. CU is also there. Change in length of steel is also there. Change in length of copper is also there. So this will become linear equation. One single linear equation with two variables which cannot be solved further. So see, if you know delta LCU plus delta LS is equal to 0.7 millimeters, which is equal to 0.7 into 10 to the power minus 3 meters. So what will be the value of delta LCU from here? Delta LCU will simply be equal to any other thing which is in millimeter? No, we have everything in SI, pascals, meter. Okay, so this becomes 0.7 into 10 to the power minus 3 minus delta LS. So what you can do in this formula, keep this as delta LS, but put this as 0.7 into 10 to the power minus 3 minus delta LS. Now this is linear equation, one variable. You just have to find out the value of LS. Once LS is found, the question was calculate load, that is force. So you can put it in any of the formula, get the value of the force. This is how you have to go about. Just remember one more thing, when you are calculating the area, for area, it is pi r square. So diameter that is given to you is 3 millimeters. Radius will be 3 by 2 millimeters, which is 1.5 millimeters. So when you are finally substituting, this will be 1.5 into 10 to the power minus 3 meters. Substitute this and then get the value of area back. Once you have area, use any formula. Let's use copper. Force you have to calculate. Length of copper is already given 2.2. Delta LCU you will calculate from the equation, and area will be pi r squared. Like this, you have to get the value of force. Harsha, tell me, this question is clear to you? How to solve it?
Yes, ma'am.
Okay, note it down. Let me know what's your answer coming.
Ma'am, can you scroll down?
Done, Harsha?
Ma'am, I'm just inserting the value.
Okay. All right, Harsha, in the next class we'll discuss. Please just calculate and let me know. Directly tell me the value of force that is coming. All right, next class we'll discuss on Thursday. And we'll try to complete with the lesson. Now, one question from Young's modulus. Then two more moduli you have. And then this stress strain curve is not in your syllabus.